Good morning and welcome to Listen to the Whispers. First off, I'd like to apologise because this talk was not meant to be virtual, but my baby daughter arrived 6 weeks early yesterday morning, so this wasn't the ideal time to fly to Las Vegas. Thankfully everyone is well, so I do have a little time to talk to you guys about timing attacks. Timing attacks can evoke some strong emotions. They take you into this world where everything is possible in theory and nothing seems to work in reality. They leave you asking, how can something be this powerful and this useless at the same time? How can there be so much research on this topic and so few people applying it day to day? It must be some kind of researcher trap. And after 10 years of avoiding this trap, I decided to step on it and see what happens. The start was painful. Timing attacks are about answering difficult questions, and I started this research with one question in mind. Does the target website contain a password reset token with a particular prefix in their database? In theory, if I try to guess a password reset token, then the time that the application takes to compare my guess with the genuine token in the database should be measurably different depending on how many characters I got right. And so using those measurements, I should be able to guess the secret token one character at a time, hijack arbitrary accounts on arbitrary websites, and generally have a good time. Now, I'd seen one write-up using this technique on a real website, so I started out by trying to replicate that, only to realise that the entire write-up was actually theoretical. They never made a proof of concept. So I thought, okay, I'll build my own vulnerable system and test out the hack concept on that instead. And I built the system just fine, but the attack just wouldn't work. So I thought, okay, maybe I built this system wrong, and I found a lab built by someone else, and the attack worked really well on that lab. In fact, it worked so well that I became a little bit suspicious and decided to look at their source code and discovered that their string comparison function was not entirely realistic. And that added sleep statement was the only reason that my attack actually worked on that lab. So I'd still proven nothing. At this point, as a last resort, I decided to cheat as much as possible, and I built a local benchmark that made tens of millions of measurements on my own system, and the attack still failed. That really didn't work out, but it hammered home this concept of the timing divide, the gap between the theoretical threat and the real threat, between the techniques that work inside someone's head, the ones that work in a lab environment, and the ones that actually work in the wild. No other web attack class has this dramatic split between the theoretical and the real, and the most interesting part of this split is the boundary between the two. If we zoom in on it, then we can see that there's this huge gap that's potentially full of undiscovered viable techniques. And we know that somewhere in this zone there's a cutoff below which the techniques don't work because the time gap is too small, but we don't know where it is. Now, during my research, the smallest time difference that led me to a real finding on a live system was 200 microseconds. That's 0.2 milliseconds or 0.0002 seconds. So we've got a lot to cover. I'm going to start by showing how to make timing attacks that work everywhere. Targeting one system is okay, but targeting arbitrary systems with no configuration required is a lot more fun. Then I'm going to introduce 3 novel timing attack techniques, each one of which has been tested on tens of thousands of live websites with bug bounty programs. All the techniques come proven with real-life case studies and accompanied with free automated open source tooling in order to leave you equipped to apply these techniques yourself next time you look at a website. After that, I'll launch the CTF, talk about defense, wrap up with the key takeaways, and I would have taken questions if this was life, but unfortunately no. But if you do have questions, just ping me on Twitter or chuck me an email address. Chuck me an email, you'll find my address at the end of this presentation. So how do you make timing attacks that work everywhere? Well, timing attack success comes down to the balance between two key variables. The signal, which is the size of the delay that you're trying to measure, and noise, which is everything else that affects the response time. If the signal is too quiet relative to the background noise, you won't hear it and the attack will fail. You can split noise into two parts, network jitter and internal jitter. Network jitter is already absolutely notorious for making timing attacks fail. When someone sees a timing attack demonstrated against a local system and says that will never work on a remote target, they're basically saying that network jitter is going to make that attack impossible. And 5 years ago, that might have been true. But with HTTP2, network jitter is dead. Web timing attacks are effectively now local because a paper called Timeless Timing Attacks showed that HTTP2's concurrency features mean that you can place two requests in a single TCP packet or TLS record, and the server will process those at the same time, effectively eliminating the effect of network jitter on timing attacks. That, by itself, is absolutely huge. And during this research, I realized that we can make this technique even better because it does have one catch, which is called the sticky ordering problem. Because both of these requests are on one TLS stream, ultimately one of them has to come before the other, and virtually all websites, all web servers have a bias towards processing the first request first. The authors of the paper address this by adding extra query parameters to the first request only so that it would take longer to process and maybe get back in sync with the second one. But I found that approach has issues which make it unsuitable for use in the wild on arbitrary targets. What we'd really like is a universal solution. And we almost already have one. Last year, I developed the single packet attack, which is a variation of the technique we just saw, but it withholds a tiny fragment of each request and places that in the final packet to trigger processing. The goal of that was to complete 20 requests with the final packet in order to trigger race conditions better, but coincidentally, if you only send 2 requests, it makes the final packet really small, which reduces the TLS decryption time and therefore helps solve the sticky ordering problem. Unfortunately, that technique is not quite generic because some servers, including some major ones, like to start processing requests as soon as the headers arrive. And some of them will even reply to your request before you've finished sending it. Now, to handle those systems equally well, we need to coalesce all the request headers into a single packet. So this way, we're sending 2 synchronized packets, and whether the server waits for the last packet or starts execution on the first one, we'll get synchronized execution. Making this happen turned out to be extremely easy. What we see here is the algorithm for the original single packet attack, and all you need to do to make that coalescing happen is add an extra ping frame. This initial sacrificial packet acts as a clue to the operating system that we'll be sending a bunch of packets soon and it's time to start coalescing. That enhanced version makes the technique twice as effective on my Nginx testbed, and it's already available in Burp Suite, and I've been working with the maintainer of the open source alternative H2 SpaceX to get it there too, so I believe that will be released this week there as well. So, now we've solved network noise, that just leaves server noise. This should not be underestimated. It can come from many places, including load on the target server, load on other systems the target server interacts with, and even other virtual systems running on the same physical hardware, such as you may get in a typical cloud environment. The best way to tackle server noise is to accept it and amplify the signal so that it still stands out. For example, Say you wanted to do that string comparison attack to test if the website supports a header name that starts with x-u. If, instead of sending that header once, you add a few hundred headers with the same prefix, then the signal becomes hundreds of times easier to detect. You can take things even further than that and adopt a denial of service mindset using techniques like nested XML entities and GraphQL batching to create a massive signal that will work on any target regardless of the noise. Ultimately, a denial of service is just a really easy timing attack. On the flip side, you can try to reduce the server noise. This is quite tricky, and you'll never get rid of the noise entirely, obviously, but the main approach there that I had success with was using repetition in order to exploit performance features such as caching that the developers made to make their website go faster. If you embrace those, then the server will spend less time processing your requests and therefore it will be less exposed to server-side noise and your measurements will be more reliable. In some cases, you can also make this happen by doing stuff like chopping bits out of your request that might make the server do extra unnecessary processing, or even hypothetically adding things like a do not track header that might make the server do less processing on your request. Now, those techniques and principles taken together make timing attacks reliable and also fast. I only had to send 5 request pairs to most targets during this research, going up to 50 if I found something that looked promising and wanted to confirm it. As far as analysis of the response orders and times goes, ParamMiner will take care of that for you. But if you prefer to experiment, you can do that with Turbo Intruder, which will give you output that looks something like this. The main thing to note here is that when you're doing an attack over HTTP2, you need to look at the response order to work out if you've got a measurable timing difference, and when you're using HTTP1, then as with a classic timing attack, it's all about the response times. These two examples here also show the power of the single packet attack because they're both run on the same target trying to detect a delay of 0.05 milliseconds. So you can see the single packet attack has reliably seen this and the response time analysis has failed. That is the foundation of timing attacks that work everywhere. The part that there's no formula for is choosing the question that you want to answer. I started this research by looking at asking questions for parameter discovery. Vulnerabilities often lurk out of sight in overlooked or forgotten features that can only be accessed via hidden parameters. So to find those parameters, you might use a tool like ParamMiner, which guesses parameter names or header names and looks at the response to see if they change the response. And it uses that to recognize them. So if a valid parameter doesn't change the response, it won't get detected. For my first bulk timing attack, I decided to try and fix this, so I took ParamMiner and I made it look at the response time as well as the response contents, and then just ran that on my pipeline of 20 to 30,000 bug bounty websites. And to my surprise, this actually worked. It revealed tons of parameters and headers that I would have never have found otherwise, including some completely crazy ones that I still have no good explanation for, such as a web server that took 5 milliseconds longer to respond to requests containing the mystery HTTP header common config, unless the header value was valid JSON. It even detected a header on another site that never actually sent me a response. It always reset the connection, but it took longer to reset the connection if you sent a certain header. And it also found some really useful stuff too. Here's one of the more useful findings. What do you think is happening here? When you see a massive time gap like this, then that can indicate a cache. And in this example, we can see that changing the value of the ID parameter is causing a cache miss. but changing the value of a random parameter isn't. So that tells us that they're only including certain parameters in the cache key, which means two things. One is that they're at major risk of web cache poisoning vulnerabilities, because that type of configuration is just extremely dangerous. So it's definitely worth looking for those on a target like this. Also, because they've added the ID parameter into their cache key, that gives us a massive clue that they're highly likely to support a parameter called ID on a different page somewhere on their website. So in effect, with timing, you can sometimes detect parameters on different pages. The challenge that I encountered with these results came from somewhere completely unexpected. I thought it was going to be noise causing false positives, but the hard part was actually that time analysis is almost too powerful. Because almost everything causes a time difference, then it's really easy to let your own assumptions lead you to the wrong conclusion about what the actual cause of a given difference is. And to illustrate this, I'm going to do a demo. In the spirit of this presentation, it's going to be targeting a live remote system using the Wi-Fi in this office, which is probably better than the Wi-Fi at DEF CON. This target doesn't even support HTTP 1, so we're just using the old school timing based technique. So here's the request to the target, and if we send this a few times and look at the response time in the bottom right corner, which is very small, we can see it's coming back in about 160 to 170 milliseconds. The fastest response I've seen is 165 milliseconds. Now, ParamMiner noticed that if you send a parameter called exec, the response takes slightly longer to come back. So if we send this now, we can see it's taking about 5 to 10 milliseconds longer to come back. So at first glance, you might be thinking, oh, their website supports a parameter called exec. Maybe they've got a nice backdoor, and maybe we've got remote code execution really easily on this target. And unfortunately, that's not the case. If it was, I wouldn't be using a live target for a live demo. What's actually happening here is that this is a web application firewall. We can see this from how if we send this payload, they reset the connection. They just drop the request and they don't reply to it. And another clue that this is a web application firewall is that ParamMiner spotted this behavior with multiple similar other parameter names such as eval. So you could be like, okay, well, they're just doing more analysis on requests that contain the exec key. That's just a WAF, that's boring, and I'm going to move on. But I thought this was kind of interesting, and I decided to ask a couple of follow-up questions, still using time-based analysis. So my first question is, well, if they take longer to process something with one parameter called exec, what if we send 10 parameters called exec? Does the delay stack? And the answer, as you can see here, is yes, it does. They're now taking almost 300 milliseconds to process this request, which indicates, yes, they are doing extra analysis every single time we add an exec parameter. Now, you probably guessed the next question, right? Which is, okay, this looks like it might work for a denial of service, because they're probably thrashing their CPU during this analysis. So what if I send quite a few exec parameters? I wonder what happens now. The answer is yes, this response takes a seriously long time to come back. We can see that took just over 3 milliseconds. So if I send this again, we can see, yeah, it's taking almost exactly 3 seconds to come back. Now, the really interesting thing though, is if I just take this and just add a couple of extra parameters, then the response comes back significantly faster. You see it took 2.7 seconds that time, so it came back about 300 milliseconds faster, which is massive, and it's doing that every time. So just by adding a couple of extra exec parameters, we've clearly kind of tripped over some kind of threshold and hit a different code path on the server. And we know that code path gets processed slightly faster, which indicates that perhaps they're doing less analysis on our request. So you may see where this is going. The next question is, well, if they're doing less analysis, are they still going to block this payload? And the answer to that is no, they're not going to block it anymore. In other words, using nothing but time analysis, we've just found a complete web application firewall bypass. And it shows how timing analysis reveals insights into the target's control flow. Now, that bypass technique has since been found by others and is now implemented in the NoWAF tool. So that detour ended with a fairly nice finding actually, but it left me wondering how many of the targets were genuine parameters exposing real attack surface and how many were just web application firewall hallucinations. I had found too many parameters to manually investigate a good sample of them. So to prove the concept was actually working at scale, I needed discoveries that I could automatically confirm with non-timing based evidence. To get that, I decided to focus on HTTP headers that enable IP address spoofing. Here's an example detection. So we can see here, sending the true client IP header has caused the response to take 5 milliseconds longer to process, but interestingly, resending it has made the response come back faster. That is evidence of DNS caching. The reason for the delay the first time but not the second is the first time it sent a DNS lookup for that domain name all the way to the authoritative server at example.com. And the second time round, the operating system had cached that response so that network round trip between the server and example.com didn't need to happen. Now, when I did this scan, the majority of the findings of the targets found that supported true client IP had visible, audible DNS caching. And also, if I changed the domain name in the true client IP header to my own domain, then almost all of those systems caused a DNS ping back to arrive at my DNS server, providing additional out-of-band confirmation of this issue. So we can see here that DNS caching technique is working really well. But what about the other 170 sites that ParamMiner found that supported this header that didn't have DNS caching? Well, I manually sampled some of those and they do look genuine. So here's one example. What do you think might be causing this large delay when I spoof an IP address in the true client IP name instead of a host name? Here's a clue. In the site's login history, they specify each login's associated IP address and the physical location that's associated with that IP. I think this delay that ParamMiner found is coming from the server passing the spoofed IP address to a third-party geolookup service. And the reason we don't get it with a domain name is the domain name isn't a valid IP, so it gets rejected by this library, and once again the network round trip is bypassed. I got a bounty for that finding, but the real value from it was the takeaway, which is that time analysis is really good at revealing control flow changes like exceptions. That realization set me up for the next phase of this research, which is that triggering and spotting exceptions is a core part of testing for server-side injection vulnerabilities, and therefore with timing, we can do that better. Here's my first finding in this area. You probably recognize this classic SQL injection payload pair, but the interesting part is that the response hasn't changed. It's the response time that's giving the game away. Unfortunately, when I confirmed and reported that finding, it got duped, and you can probably guess why. There are plenty of people out there and scanners already looking for SQL injection using sleep statements. And that approach will find basically exactly the same vulnerabilities, but it doesn't require any advanced timing analysis. So we can infer that timing is a bad fit for finding injection into sleep-capable languages. The only time when it really adds value is if you've got something like a web application firewall blocking sleep-based payloads. But what about less powerful languages that don't let you execute sleep? Is timing useful there? Well, yeah, it's really good at it actually. Here's a blind server-side JSON injection that was detected thanks to a 0.2 millisecond response difference. The hard part with a finding like this is gaining enough understanding of what's happening on the server to actually exploit it. Here we can see from the responses there's also a client-side JSON injection, and that seems like a bit of a coincidence. So I started exploring it and noticed that if I sent a long key, then the payload that was reflected back to me was redacted. And when that redaction happened, that made the associated server-side time difference go away. So by combining that visible information about the redaction from the response timing data, we can infer that something on the server is processing the same response that gets sent to us. In other words, it's potentially a almost standalone system like some plugin analytics software or something like that that's causing this server-side vulnerability. Ultimately though, I wasn't able to find a valid exploit and had to just call it a day and move on, but at least we got some understanding of the target. The most successful injection probe that found the most issues was looking for blind server-side parameter pollution. This worked by comparing the responses for response times in reserved URI characters like hash and with non-reserved characters like exclamation mark. And once again, it's great at finding these issues, but to build an exploit for them, you almost need to know what to expect. And one thing that I found does help with that is something I'll call bug doppelgangers, which is equivalent non-blind variations of the same vulnerability. If you run ParamMiner and tell it to find blind server-side parameter pollution using timing, it will look at the responses and find non-blind ones using non-time based evidence as well. And those are maybe more likely to have already been found by someone else, but they're still really useful for kind of getting to grips with what behavior this kind of attack should be presenting to you and how to actually turn it into a useful exploit. In summary though, timing analysis is really good at finding server-side injection vulnerabilities, but the ones it's the best at finding are the hardest to exploit. The majority of the valid exploits that came from this research were found in the third phase, when I realized that you could use time analysis to detect a vulnerability class that had seemed almost undetectable to me for the last 7 years. Back in 2017, I explored an overlooked type of server-side request forgery by sending a bunch of websites a HTTP request that said, please forward this to my server, by placing my domain in the host header sent to their website. If this request then actually arrived at my server, that meant that I'd found a misconfigured reverse proxy, which I could then use to plunder the target's internal network. I had a lot of fun with that research, and I even ended up exploiting my own ISP by accident because they were man-in-the-middling me, which was rude. But I knew that this detection technique had a significant blind spot. And I'll refer to this blind spot as scoped SSRF. This is where the reverse proxy will only access subdomains of the target company. There's a bunch of ways that this can occur, but the result is always the same. You've got a vulnerability that's almost as powerful as regular server-side request forgery, but it can't be detected using DNS pingbacks because either the server won't issue a ping back to the attacker's website, or the ping back won't make it out of the server's internal network. Detecting scoped SSRF is seriously hard. Take this response sample. We can see, yep, they're doing some kind of host header validation. Great, but that doesn't tell us that they're vulnerable to anything. It doesn't tell us if they're trying to connect to the host name that we gave them. So to detect scoped SSRF, we need to ask the question, did the server try to connect to the specified host name? And timing is perfectly suited for this thanks to DNS caching. It's that easy. It's just like the IP spoofing attack that we did earlier. Well, it's almost that easy because some targets don't do DNS caching, or they don't cache the response to failed DNS lookups. But there's an alternative way of finding those targets, because DNS labels have a maximum length. And if you go one character over that length, either the DNS client will refuse to send that lookup and the response will come back faster because the network round trip won't happen, or the DNS resolver that the target is using will just time out, which will make the response take ages to come back. So using these two techniques in tandem, we can detect almost every scoped SSRF vulnerability out there reliably. To be honest, when I put this on that slide, I was like, that looks really obvious, but that's just how things are in retrospect. I know this is valuable because it exposed hundreds of reverse proxies, which in turn exposed thousands of domains. And so I decided to automate the follow-up step of exploring the target's network to find valuable internal destinations to access through that proxy. So if you run exploit scoped SSRF from ParamMiner, it will look up all the known subdomains of that target and it will try to connect to them in two ways. It will try and access them directly like a legitimate user would, and it will try and access them through the proxy, and then it will let you know if there were any significant differences in the response from the two access techniques, such as a missing header. Now that header might look like nothing, but it's what it indicates that's valuable. It shows us that we've taken a different route to this destination, and that is where things are going to get interesting later on. On the surface, this host header guessing technique is quite similar to virtual host brute forcing, but the outcomes and opportunities that it will give you are very different. So it's important to recognize it and distinguish it from just finding virtual hosts. The findings from this research fell into four main categories, and the first three of these are hilariously easy to exploit. First off, the simplest exploit is where you can see the target internal system from outside, but you can't directly access it because you've got something like a firewall that just resets your connection. For example, on one real target, I found a DNS record pointing to their SonarQube installation, but the firewall just reset my connection. I couldn't actually establish a TCP connection with that internal system, but by using the reverse proxy, I was able to defeat the firewall by going round it. That's what scoped SSRF lets you do. Any defense, you just go round it. There's a common variation where the internal system doesn't have a convenient public DNS record to flag that it exists, but there is an internal DNS record on an internal DNS server that the reverse proxy has access to. So you just have to guess the host name, and then you'll discover all sorts of things, including a vast number of pre-prod staging and development servers that can often be soft targets. But the most interesting thing that I found with that technique was pre-launch systems that were still under construction. For example, I discovered an admin console with apparently public login access on a really cool US government system that I'm absolutely gutted that I can't provide any additional details about. I reported that issue when I found it, and the system went live a few months later, and it does look like it has been patched. The admin console is nowhere in sight. I also found a very similar issue on Red Bull, which is mostly notable because they paid me in cans rather than money. Other valuable targets are publicly accessible the normal way, but they sit behind front-end servers which enforce security rules like blocking attacks or restricting access to valuable endpoints. For example, I found one internal admin console where trying to access it directly would just serve you a 403, but once again, you can use your reverse proxy to just go round. The final and most subtle category of exploit is front-end impersonation attacks. Front-end servers often add internal HTTP headers onto requests before forwarding them to the back end, and backends tend to trust these headers implicitly. This enables an attack that's kind of already known in the industry but not properly appreciated as an actual entire bug class. Everyone knows that you can spoof IP addresses using headers sometimes, but few people are paying attention to what else gets transmitted in these headers, which is often far more powerful. In theory, using headers to transmit authentication style information like this is safe because if an attacker spoofs a header, the front end will overwrite it. But if we go around the front end, we can bypass the header overwrite, impersonate the front end, and exploit this trust relationship to do some serious damage. And in addition to doing exploitation via reverse proxies, you can also exploit it via unintended direct access to the backend, or with request smuggling, which is what I used for that new relic exploit shown on the previous slide, which gave me full admin access to their core internal API. And you can also exploit it using header masking or mutation techniques as well. Front-end impersonation attacks are seriously powerful, and the only hard part is guessing the names of the internal headers that system is using, which is something that timing can help with. So that's all the techniques I have for you. We've seen timing analysis is useful for recon, reverse engineering, and finding exploits. If you'd like to try those techniques out for yourself, I've made a small capture the flag at listentothewhispers.net. There's two ways to solve this. One is with Param Miner, which will do a lot of heavy lifting for you. Or if you want the authentic research experience, you could try solving it using the new timing.py script inside Turbo Intruder. For me, this research is only a success if people actually start using their timing attacks day to day. As such, I had planned to spend the next month improving the tooling in Param Miner and Turbo Intruder, although I imagine the baby may have other ideas. But at some point, hopefully fairly soon, I am going to do that. And so if you have any requests for these tools, if you find them hard to use or have any issues or feature ideas or anything like that, please let me know. As far as further research in this field goes, I think the thing that this field needs the most is more people finding valuable questions that timing analysis can answer with practical techniques right now. I think for the last 10 or 20 years, we've been really focused on finding better time analysis techniques, and we've kind of overlooked finding the questions that are valuable. And the cool thing about that is it's also a lot easier. It's not necessarily going to be a 6-month research project just to find, make the technique 1% better. You can do this, and it's totally worth having a go. The other areas that I think are ripe for investigation at the moment are looking at things like specific frameworks or maybe servers to find, can you get signal amplification techniques that work on everything on a given framework or a given web server, because those will be really valuable and will enable a bunch of interesting new attacks on those targets. As far as defense goes, it's safest to overestimate your attacker's capabilities. For a start, Obviously, please don't use wildcard routing on your reverse proxies, just use an allow list of trusted destinations. But more broadly in general, when you're coding an application, assume that attackers have full visibility on the execution flow that your site is taking. So they can't read out your server-side variables yet, but they can see which branches your code is taking, and maybe things like how many iterations each loop goes through. If someone reports a vulnerability to you using nothing but timing-based evidence, I would suggest requesting a proof of concept, but I would always recommend patching the issue regardless, because at the end of the day, your security should not rely on noise, especially server-side noise. Server-side noise is something that will vary from hour to hour and day to day and week to week, all on a single system that doesn't even have any other live users. It should not be relied on. If you're configuring a web application firewall or web server, you could potentially use a micro throttle to make the single packet attack less effective, and that might be worth doing as a defense in-depth measure too. As far as further reading goes, there's a lot of stuff. There's a lot of places you can take this. The main link to remember is the white paper. That's the top link, and that contains a bit of extra information and also all of the other links on this slide, including the releasable source code for both the tools mentioned in this presentation. If you enjoyed this video, you may also like the talk tomorrow from my colleague Martin on web cache poisoning, which I think is going to make some CDN vendors panic, and Gareth's talk on Sunday, which will leave you terrified of email address parsing. Both those talks are really live. Go out there and say hi to them. The three key things to take away are that web timing attacks can answer seriously difficult questions. The single packet attack makes them local, universal, and feasible. And the murmurs are always out there. They're just waiting for you to listen to them. So that's it from me. Hope you enjoyed that. If you have any questions, just chuck me an email. Don't forget to follow me on X and check out the white paper. Thank you for listening.